Okay, so our next speaker is Dilip Kumar from TestSolve, where he's a design lead. 10 years of industry experience as a design verification engineer, and has worked extensively on verifying designs at full chip as well as subsystem and IPs. Has worked with leading semiconductor companies on world-class products, and has gained in-depth knowledge on the concepts of verification. He currently works as a verification consultant for Xilinx AMD and is involved in verifying the FPGA designs at full chip level. And the title of his talk is Practical Applications of Machine Learning in Design Verification, ISO 26262. Over to you.
Thanks, Mike. Good afternoon, everyone. I welcome you all to this discussion on practical applications of machine learning in design verification and in ISO 26262 standards for vehicle safety. Before we begin, let me take a moment to reflect on how TestSolve is proving its capabilities and helping leading semiconductor companies across the globe. Over the last 20 years, TestSolve has acquired deep domain expertise along various service lines such as VLSI design, PCB design, embedded system design, and test engineering. TestSolve's 3,000 plus strong workforce has more than 50% of its employees with over 10 years of industry experience. The agenda for today's discussion, we begin by discussing strategies for AI model development, and then we look at the background to identify some of the key challenges in design verification as of today, and where we think the use of AI and ML could help improve verification efficiency and reduce verification efforts and time. We'll also look at some of our own experiences at TestSolve in employing these large language models and machine learning to some of the verification tasks, such as coverage closure, debug analysis, and regression suite management. We'll also go over some of the current practicalities of using AI and ML in verification. Lastly, we'll discuss the application of ML in ISO 26262 standards to improve safety in automobiles. Coming to the strategy for AI model development, there are several strategies, but the strategy that we employed was to develop any AI model. We need large sets of training data, larger better. And then we use this training data to train the AI model. Along with this training data, we also use some recorded user prompts, and the AI model will generate results for us. The results that these AI models generate then have to be validated. For this, we use automated test data and perform validation. When we have to upgrade this AI model, when we take the untrained AI model and use a superset of existing training data and train the AI model quickly to see better accuracy in the results that are being generated by this AI model. Currently, all the validation that is being done to these AI models is being done manually. A quick overview of the historic summary from the previous Verification Futures conference in identifying some of the key challenges in verification. As we can see from this table, we see some of the key challenges are complexity in the design, debug analysis, and resource allocation. One of the key challenges that is being addressed today is the safety verification, where over 40% of the chips that are being designed today are safety critical. Another key challenge is the security verification, where close to 60% of the IC designs today are incorporating additional security features for enhanced security in the design. A new entry to this list of challenges is use of AI and ML in verification, which will be the focus of our discussion today. Let's look at the experiments that we at TestSolve have done in employing AI and ML in IP level verification. Conventionally, for any IP verification, the flow we follow is we analyze the spec, we generate a set of features that have to be verified from the specifications, and also develop a coverage plan. Once we have this coverage plan, we then proceed with the test bench generation, test component generation, and test sequence generation to verify the features that have been identified. And we also do constraint generation for better randomization and improved coverage. And once we have the setup, we proceed to run the simulations and then debug the failures. So in this conventional flow of IP verification, we took the help of AI and ML in certain aspects of this verification, where for the first specification analysis and feature extraction and coverage planning to develop the verification plan, we took the help of the large language models. And for test bench component and test sequence generation, we use some of the scripts for automation. And for constraint generation, also, we took the help of large language models. And for simulation debug purposes and regression suite management, we took the help of machine learning. A simple example of how the AI model was used to analyze the specification and extract some of the features for verification. The specification that was input to the AI model was of a synchronous FIFO from Xilinx. The AI model was able to analyze the specification and extract a set of features that have to be verified. For example, the data read and write operations, verify the data that is incoming into the FIFO on the DIN port when the write enable is asserted is correctly written into the FIFO memory locations on the rising edge of the clock. Similarly, the read operations to when the read enable is asserted, make sure that the data that has been written into the FIFO is read exactly in the same order. Another feature is the verification of the status flags like FIFO empty, FIFO full conditions. And another feature is invalid request handling to verify that the FIFO status is not corrupted when an invalid write or read request is issued. The large language models, we can also take the help of these AI models for coding assistance. In our case, the AI model was able to generate a simple directed test bench to verify some of the features of the FIFO. For example, in this, we can see that the AI model was able to give us a simple directed test bench where the features like reset and a write operation followed by a read operation was generated by the AI model. Similarly, this large language models can also help us generate some of the assertions and cover groups along with cover points, as well as cross coverage between these cover points. A quick look at the numbers on one of the pilot projects we at TestSolve we use the help of AI and ML. Conventionally, for these aspects in verification, like specification analysis, conventionally what would take 1 week for one engineer could be done in 2 hours with the help of AI. Similarly, for feature extraction, what would conventionally take 2 days for one engineer could be done in 1 day with the help of AI. Similarly, for other aspects such as constraint generation, coverage generation, assertion generation, and UVM template generation, all of these tasks can be seen great reduction in the number of hours and efforts with the help of AI. A graphical view of saving on hours with the help of AI. The orange graph here shows the conventional number of hours for each of the specific tasks in verification, and the blue graph shows the amount of hours that is needed with the help of AI. Conventionally, for all these aspects put together, what would have taken over 100 hours can be achieved, can be done in under 20 hours. The results, that is an astonishing 85%, up to 85% savings in the efforts in verification. Applying machine learning for debug analysis. Whenever we see failures in regressions, like the key indicators from the code source to identify the root cause of the problem would be to see what was the time a file was checked in, how many editors were there to that file, and were there multiple files that were checked in together, and history of bugginess to the file. Was this file cause of failure in the past, and who made the commit? Once we have this data, right, we can train the AI model and indicate where to start looking to identify the root cause for debug. And when there is a history of bugginess to the file, before a file has to be checked in, should we run more check-in tests? Or should we review some of the riskiest commits to this file and use of linting for design and test bench codes? Coming to the practicalities of using AI and ML in verification, there are 3 practicalities. One is understanding how and where we can use this large language models to improve our verification efficiency. The second practicality is the size of the data sets. Like I said before, there is the larger the data set to train the AI model, the better efficiency we would see in the AI model's results that are generated. So the large data sets that we need to train this AI model has to be clean and unbiased. We have to ensure that the data that we are using to train the AI model is clean and unbiased. The third practicality is security. Can these large language models use the cloud normally without compromising on data integrity and data security? Coming to the ISO 26262 standards for automotive functional safety. ISO 26262, as all of you would be aware, is an international standards that defines functional safety for electrical and electronic components employed in an automobile. This ISO 26262 standards is a framework, is a set of guidelines that to ensure that the safety-related systems that are used in automobiles function reliably and safely throughout their lifetime. The potential hazards in an automobile are rated on different levels, taking into account three main factors, such as the severity of a potential hazard, the controllability factor, and the probability factor. How often could a failure occur in the future? So based on these factors, the hazards are given ratings on different levels called ASILs, automotive safety integrity levels, A, B, C, and D, A being the least hazardous condition and D being the most hazardous condition. There's also a fifth one called quality management, which is assigned to non-hazardous systems in automobiles like Bluetooth and GPS navigation and so on. At TestSolve, some of our engineers have been actively working on developing an AI expert for FUSA. And one of the use cases from this FUSA AI expert is the determination of the ASIL rating. When we ask the AI expert by providing a potential hazardous condition, like what is the probability of a brake failure when a car is being driven on an expressway at night when it's raining and the speed is about 120 kilometers per hour. Based on this, considering the three factors, severity, the AI model was able to rate the severity as S3 and exposure as E4 and controllability as C3, which translates to ASIL-D, a very hazardous condition. It is indeed, if we are driving a car in expressway at that speed at night when it's raining, it is potentially hazardous condition, life-threatening. Another use case is ASIL decomposition. ASIL decomposition is a process which involves breaking down of a high ASIL rating feature into lower parts and functions, where each of these smaller parts and functions will have lesser ASIL rating. So we asked the AI model, what are the three advantages of ASIL decomposition? The AI model generated the answer saying reduction in cost, enhancement in the safety, and flexibility in design. This table shows us what are the probabilities of ASIL decomposition. ASIL-D, for example, can either be downgraded to one ASIL-C and one ASIL-A requirement, or two ASIL-B requirements, or one ASIL-D and one quality management, so on for different ASIL ratings. Another use case is hazard analysis and risk assessment. When we provided some of the potential hazards, described the potential hazards, our AI model was able to provide the severity, probability, and controllability ratings along with the ASIL ratings and give us a safety goal and a way to ensure or achieve this safety goal. For example, if you see the first condition, the probability of both headlights failing simultaneously at the same time when both the headlights fail. The ASIL rating is ASIL-C, which is pretty hazardous. And the safety goal would be to make sure that both the headlights do not fail at the same time. And the safety measure, how do we ensure that this does not happen? By using redundant power supplies and independent control circuits for both the headlights. Similarly, when we describe other potential hazardous conditions, our AI model was able to generate the ratings, provide us the safety goal and the safety measure. Not just this, another use case is the safety mechanism recommendation that the AI model was able to provide us. When we asked what is the safety mechanism for the phase lock loops, the AI model gave us a list of safety recommendations like frequency monitoring, lock detection, redundancy, periodic self-checks, and voltage and temperature monitoring to make sure these are within the levels of operation at all times. Another example is the safety mechanisms for the mostly used SOC components, such as microcontroller, memories, communication interfaces, power management, GPUs, and so on. Our AI model was effectively could give us safety mechanism recommendations. In conclusion, the use of AI and machine learning can definitely and will definitely change the way we are currently doing verification. The results are promising with certain aspects like specification analysis, feature extraction, test bench infrastructure development, and so on. Currently, the EDA tool manufacturing companies are using or employing these AI and ML under the hood to improve the use of these tools for better efficiency in verification. Some of the challenges, though, are accuracy of these AI models, the rigorous validation that is needed to ensure that these AI models are accurate, and reliability factors of these AI models over time, the data security, and a standardization for GenAI usage. Currently, there is a research on AI-assisted research that is going on DVFlow on different aspects such as AI model training, model building, model performance assessment, GenAI RAG applications, GenAI applications, AI agents, and so on. TESOLVE is open on research for these topics. If anybody is interested to join the task force, please write to mike.bartley@tesolve.com. Thank you. That was my presentation.
Thank you.
Any questions?
We have one question from the audience. Can you introduce yourself first as well, please?
Hey, is this on?
Yes, yes.
Okay. My name is Karthik Nanda with L&T Semi. On slide 9, when you were talking about spec, I guess spec understanding, conventional.
This one?
No, two forward. One more. Yeah. So conventional effort versus the AI-assisted effort. You're showing how AI can be a lot better at analyzing a specification in terms of time. How about accuracy? Does the AI actually miss something that an engineer would have found?
That's a bad question. Accuracy is always, a point of question for when AI models are being developed. Like we discussed, these AI models have to be trained, so we have to use sets of training data, right? The more the data that we use to train these AI models, we can see the better accuracy in the results. So similarly, for you, in your question, specification analysis, we have to train these AI models over time to do some specification analysis. And when it generates a list of features, when we see the human intervention, of course, is necessary. When we see that there is a feature that could have been extracted by the AI model and which it did not, we have to then train the AI model to improve its accuracy the next time over.
Larry's got a question. Before you speak there, I'll just come back on, because I've been working on this. Derek's done the presentation over at the PPT. We've been working on this for about 9 months, a year now. And when we first started, we were sort of analysing one chapter at a time. And the feedback from the customer, the people we're working with was, can you make it more complex? So we're now looking at specifications that and generating assertions and coverage points that will span 5 or 6 chapters at a time. And the complexity has gone up, but the accuracy is still there. And we do a lot of manual validation where we say to the person, did we miss anything? And they compare it. A lot of the time you're doing the analysis on work that's already been done. So they say, oh, we missed that one, or there's a coverage point we didn't see. So there's still a lot of manual validation goes on, but it's the accuracy is improving.
So this in progress.
Yeah, but well, I'm not sure it'll ever not be work in progress because it's just constantly trying to improve and evolve those models. Yeah. Sorry, Larry, go. Okay. You'd be stealing from your own time anyway. No. Okay. Thanks, Dylan.
Thank you very much, everyone.
Thank you.